The following program has been made possible by a grant from Champion International Corporation. For 7 years, a great drought has afflicted Africa. Where crops once ripened, fields have turned to dust. Millions of people retreated before the advancing desert. But in 1974, an eye in space observed the life-giving rain clouds once again spilling deeper into Africa. The machine that makes the world's weather keeps changing gear. The weather satellite shows a planet that grieves for its lost harvests, while the price of food keeps going up. Good evening. Are the better rains of Africa a sign of hope, or just a deceptive pause in the southward march of the Sahara Desert? At any rate, the Earth's climate is varying in little ways that may spell big trouble for all of us. The rain's been desperately late in coming to the parched farms of India, while nearby Bangladesh was awash with fatal floods. What's happening to the monsoon that feeds half of Asia? Again and again, the newspapers and television have been reporting weather disasters. In 1974, the Midwest suffered its worst drought since the 1930s, and deadly tornadoes were on the rampage. But we'll find, strange to say, that the Japanese actually welcome the great typhoons that bring floods to their country. And we'll examine why so many places have been having cool and dismal summers. The weather machine's an all-embracing system of air and water and ice, three fluids that work together between the tropics and the poles and govern all our lives. In this program, we'll visit the frontiers of present knowledge about our ever-changing weather. We'll go, for instance, to the tropical Atlantic, where 40 research ships from 10 nations have spent the summer. Because it's sunny or wet, warm or cold in North America today, according to what was happening in the tropical air last week, in the oceans 2 weeks ago, and in the polar ice many centuries ago. Here's where we begin, in the barefaced ice of Greenland. In the great ice sheet that buries Greenland, the snowfalls of 1,000 centuries are piled up to 2 miles in thickness. The air's thin here, and remote from anywhere in the fastness of the ice, men have planted a frail encampment. They're drilling for ancient ice deep under the surface. The deeper, the older. An earlier drilling at another site went right through to the bottom of the ice. This time, they're going down just 1/4 of a mile, through 1,400 years of compressed snow. Nowadays, men can tell the climate of past centuries from a piece of ice. That's why they've come here, to a ridge of the ice sheet at a map reference known as Kret. In 1974, polar engineers of the U.S. Army and scientists from Denmark and Switzerland have been sharing the work around the clock under the unsleeping sun of summer. In this season's drilling, the oldest ice recovered is more than 14 centuries old. The snow that made it fell shortly before the birth of the Prophet Muhammad. As one team of scientists takes over from another, some of the ice samples go to Denmark. But where are the snows of yesteryear, a poet wanted to know? They're here, in cold storage at Copenhagen University. The Pope was grumbling that the sea ice had stopped any bishop from visiting Greenland for 90 years when these snows settled on the ice sheet in 1492. In fact, his Norse congregations had perished long before. But how can you tell of changes in the climate just from the ice? One piece looks very much like another, especially when they're melted. But this laboratory's business is to weigh the atoms of oxygen that the ice contains. First, the melted ice swaps oxygen atoms with carbon dioxide gas. When the gas has a fair sample of the oxygen atoms from the Greenland ice, a powerful magnet sorts them according to weight. The amount of the rare, heavy sort of oxygen is what matters. The heavy oxygen varies from layer to layer, century to century. More of it found its way into the Greenland snow whenever the world was warm. In very cold times, the heavy oxygen was scarce. So, the Danish climate hunters make thousands of measurements from different drillings while they unravel the age and history of each piece of ice. As the computer puts together the results from consecutive samples, the younger ice reveals even the changing seasons year by year. The heavy oxygen rose to a peak each summer. Then it fell away again in the winter. It's a great help for accurate dating. For Willie Dansgaard, his laboratory is a time machine. It recaptures the climates that our remote ancestors knew. In Napoleon's time, it was a good deal colder than the 20th century. It was colder, too, in America's early colonial days. And in William Shakespeare's winters, milk came frozen home in pail. The Little Ice Age, it was called. But the Vikings made their forays when northern lands were much warmer. The cold came and went. The Roman Empire flourished during another warm spell. And so, long before it, did the Egypt of Tutankhamun. But if we go further into the Greenland ice, more than 10,000 years, we're deep into a real ice age. Our ancestors who made this goddess 30,000 years ago faced the big freeze that began long before. The Copenhagen physicists think they see, during the last 8 centuries, 2 separate rhythms of warmth and cold. Add them together, and the match is quite good. It's cooling now. If those rhythms are real, you can make a forecast. Chilly for 100 years, then warmer, perhaps. But 200 years hence, cold again. It's only a half-joking forecast, yet it tells of an inconstant climate that could alter all our lives. Just how reliably do the Greenland snows register the changing climate? Are the rhythms real? The drillers go again and again for checks on the bleak forecast. Far below, an unseen land sags darkly under its burden of ice. And around the edges of the ice sheet, the glaciers, sluggish rivers of ice, lick the landscape with their frozen tongues. Nature's ice dwarfs us and outstrips our own efforts to alter the planet where we live. The ice can seize or release huge areas of land and affect the climate even in much warmer places. Besides the risk of somewhat cooler weather in the decades ahead, there's the ever-present threat of a big freeze. Will a new ice age grab our lands and erase our northern cities? It's buried Manhattan Island before, when great glaciers half a mile thick filled the valley of New York's Hudson River. That's what an ice age is all about. George Kukla is from Czechoslovakia, where he discovered signs that ice ages are far more frequent than most experts have supposed. Today, he continues his work near New York City as an exile. For him, the next ice age is not at all remote.
Well, almost all of us have been pretty sure that there were only 4 ice ages, separated by relatively long warm intervals. But now we know that they were 20 in the last 2 million years. And the warm periods are much shorter than we believed originally. They are something around 10,000 years long. And I'm sorry to say that the one we are living in now has just passed its 10,000 years birthday. What of course means that the ice age is due now any time.
The threat of ice is another of our themes this evening. Not only New York, but most of North America was buried during previous ice ages. This could be a postcard of Chicago when that happened. And here's how Los Angeles would have looked in an ice age. Right now, we're living through a period of cooling. But before you sell your house and head for sunnier climes, scientists think it's much less likely to be the start of the big freeze than a return towards those cooler conditions our forefathers knew. A little ice age. Of course, that's bad enough, particularly in our era of expensive fuel and scarce food. Hindsight now tells us that in the 1940s, the world was warmer than at any time for almost 1,000 years. Many of us are old enough to remember those sweltering summers. But since then, our northern countries have become cooler. The armadillos of the Midwest have shifted south, apparently on account of the cold, while the snow geese of the Arctic have found their breeding grounds obliterated by snow that lies all summer. For European farmers, the growing season has become shorter. Another change is that there's too much rainfall sometimes in parts of North America that were persistently dry in the 1930s. All of these occurrences are linked because the weather machine works as one system. Its chief job is to hold back that polar cold by spreading the heat of the tropics. The air is the first of its working fluids. The whirling movements you see in these satellite pictures are produced by the spinning of the Earth, but the sun's rays drive the whole machine. They're absorbed by the water and the land, which then heat the air from below. High up, the air's cold. Among the main features of the weather machine are the great clusters of clouds in the tropics. Yet they went almost unrecognized until satellite pictures showed them strung across the oceans. The clouds are signs that the air is rising. The tropical oceans are the Earth's chief boilers that keep us all warm. And the cloud clusters pump billions of tons of air sky high. It starts off towards the poles, but it soon comes down. Sinking air makes no clouds, no rain. So this is the zone of deserts. Then the air flows back through the tropics at the surface as the trade winds. Meanwhile, cold air from the Arctic is seeping southwards, as if trying to chill the world. In between, the contrast between warm tropical air and cold polar air powers a jet stream. It sweeps warm air northwards and cold air southwards as it zigzags around the world. 6 miles above our head, it blows at hurricane force. Changes in the routes favored by the jet stream help, as we'll see, to alter the climate. Because at the Earth's surface, great eddies of air are related to the jet stream. They make the characteristic weather of the stormy zone in which we live.
In the stormy zone, a clockwise whirl in the winds marks an anticyclone and a spell of fair weather. Where the winds revolve the other way, it's a depression, where rising air makes clouds, like the clouds that a satellite sees in a depression that's nearing the British Isles. The storm is busily exchanging cold air for warm air. It's sweeping heat toward the Arctic. It all helps to ward off the next ice age, if you can look at it that way, when life is in danger at sea. But the price of warmth is too great for some. While human beings pay with their lives for the real weather, a mathematical model of this storm is raging in the circuits of a computer. It says the storm is shifting away. One storm is moving off, but there's usually another on its way. Weather news from all around the world provides raw material for the computer. Forecasts by computer aren't mysterious. To the weather information it received, the computer applies laws. About the air moved by heat, pressure, and the spinning of the Earth. About moist air turning to rain. The British Meteorological Office was the first to adopt the new generation of very powerful computers for routine forecasting. This display is the next step. It's intended to let experienced humans prompt the computer. A storm in the Atlantic, as visualized by the computer, doesn't seem to be intense enough. That's probably because too few observations have come in from the middle of the ocean. Another pressure line makes the storm deeper. The worldwide information is barely in before a forecast is due. The computer reckons the likely changes right across the northern hemisphere at 10 different levels in the air. It's a race against real events, so imitating the weather by numbers can only be approximate. 20 minutes figuring, that's all the computer's allowed to produce its predictions for tomorrow. And after doing 20 billion sums, the computer offers its forecast for the whole northern hemisphere for 3 days hence. There's more to come. So far, the computer has calculated at 3,000 points across the map. That means not many points on Western Europe, only about 50. Now the net's drawn tighter for the rainfall. More detail, more arithmetic. Forecasts of the weather high in the air usually go to the airlines untouched by human hand. For the weather on the ground, too, you don't alter the computer's forecast unless you have to. But human forecasters know the quirks of the weather, about the sorts of error the computer tends to make, and about small events like thunderstorms that the computer overlooks. The computer's more skillful, though, at grasping overall weather patterns. Together, man and computer have a partial comprehension, not always certain, of the daily weather. But it all depends on that worldwide information. When it's midnight Greenwich time, it's mid-morning in the Western Pacific. Beyond the ocean is a world that waits for news from the atoll of Truk. The weather observer's main tool is a little package of expendable instruments measuring pressure, temperature, and humidity as it rises in the air. It'll go up 20 miles. The same thing's happening in Africa. At noon and midnight Greenwich time, 700 balloons sample worldwide the weather of the upper air. As this balloon rises over Hong Kong, it carries a radar reflector. Tracking it reveals the winds blowing high overhead. World Weather Watch, they call it. Flyers report the weather en route. They know the value of reliable forecasts.
We estimate ACAP 47. Outside temperature -37 Charlie. Spot wind 230 diagonal 25.
And 7,000 merchant ships fill awkward gaps in the reports from mid-ocean. The pooled weather news flashes to every country, normally within 3 hours of the observations. It's routed through communication centers like the one in New Delhi. In free exchange for the weather reports, forecasts like this one made by the Indian's computer go electronically to any country that wants them. Nothing unites the nations like the war against bad weather. A cold front is edging out of China, but the news came well ahead of it. For nearly 20 years, despite the Cultural Revolution, despite wars in Asia, weathermen in Hong Kong have received meticulous balloon reports from China. They come in 4 times a day. And every day, from an American satellite, a gift of pictures. For 8 years now, anyone in the world has been able to receive automatic picture transmissions from our weather satellites. With a simple ground station, you just point your aerial to where the satellite's passing overhead. In this part of the world, the chief worry for weathermen is typhoons. Hong Kong is a small target on the China coast, but every few years a ferocious storm slams into the city. Refuge harbors are not a luxury. A modern radar gives precise details about an incoming typhoon. It need no longer surprise and kill, but the early warning comes from the satellite. The pictures cover 20 million square miles around Hong Kong. They're normal today. But they always check for anything that looks like the sinister spiral of a nearby typhoon.
Here's a model of a modern American weather satellite that broadcasts its pictures to anyone who wants them. There are strategic gaps in the World Weather Watch, especially in the tropics, the southern hemisphere, and the oceans generally. The hope is that satellites will fill in some of these blank spots. This one already carries infrared instruments that detect the Earth's heat rays. They tell the temperatures of the cloud tops and of the sea, and they even monitor the weather at night. This satellite orbits over the poles, and as the Earth rotates, it visits each part of the world once a day and once a night. But other satellites orbit in step with the spinning Earth and give non-stop observation of one huge area. The latest of that kind is called GOES, G-O-E-S. That stands for Geostationary Operational Environmental Satellite. It scans the light and heat rays from the Earth, building up pictures every half hour. Satellites are to the weathermen as the telescope was to the astronomers. They stand at the window of the weather machine looking in, and they show on nature's weather map what's happening over whole oceans and continents and encompass storms too wide for any ordinary eye. As satellites take their place alongside computers as powerful scientific tools, the meteorology of the 1970s can deal quite well with large-scale weather systems that develop over a few days. But the weather machine operates on many different timescales, from thousands of years for making or melting great ice sheets to the fleeting lives of individual clouds. To a large extent, clouds are the weather. So how well do the weathermen understand the clouds that show up fuzzily in the satellite pictures?
The United States, May 24, 1973. Between scattered clouds, Oklahoma bakes in the morning sun. Many farming communities, like Union City, population 300, lie scattered in a broad zone of North America where thunderstorms bring special dangers. Here, meteorologists shot unique film on that Thursday afternoon of what happens when colliding squalls set the base of a cloud spinning and seething. A tornado was born. It tore Union City apart in a matter of minutes. Astonishingly, perhaps, only 2 people were killed, but it caused $1 million worth of damage in this one small town. 1973 and 74 were America's worst years for tornadoes on record. And a tornado-chasing unit, armed with radars and cameras, watched as pieces of Union City were flung about like leaves. The deadly violence of these storms remains puzzling. To imitate the action of tornadoes, Ted Fujita runs a machine at the University of Chicago. Its revolving cups force the air to spin. Dry ice in water forms a fog to make the vortex visible, while suction through the hood draws the air upwards. A strong updraft and rotating air. By the usual theories, that's the recipe for making a tornado. Fortunately, it's not the whole story. Otherwise, tornadoes would be far commoner than they are. Apart from the obvious vortex, there's an invisible process going on even in the model tornado. The machine shows a curious effect. Put on too much suction, and the tornado collapses. Reduce the updraft again, and it recovers. So what really keeps a tornado going? It seems to be a current of air that comes downwards around the outside of the vortex. Block off that fast downdraft, and you kill the tornado. So let it flow again. Professor Fujita's theory is that sometimes a sudden unseen draft of cold air drops from the top of a rotating thundercloud. That may be what sets a real tornado going. Research into causes of tornadoes should make them more predictable. It's already helping save lives. The prime agents of the weather, the clouds, appear when moist air rises and cools. They lie between the level where the air becomes too cold to keep its water vapor and the bottom of the stratosphere, which is a kind of lid. In relatively warm air, water droplets make puffy clouds. In colder air higher up, ice crystals form and the clouds are streaky. Most of the world's rain is melted snow. But first raindrops and then snowflakes can form only with the help of minute particles of dust in the air. For instance, salt spattered from the ocean, or dust from volcanoes, or even smoke from a car. Sometimes a cloud may contain water all ready to form more droplets or ice crystals, but which doesn't do so because it hasn't had enough of the right sort of natural dust. You can then try to encourage rain by seeding the cloud with special materials. The discovery that humans could really affect clouds was made by this American. Nearly 30 years ago, Vince Schaefer was in his laboratory making clouds. It was a hot day, so he grabbed some dry ice, frozen carbon dioxide, simply to help cool his freezer. But doing that transformed the cloud. Water droplets, already chilled, froze into sparkling crystals of ice. Even the smallest pieces of dry ice did the trick. Later, he dropped dry ice pellets into a cloud over Massachusetts and transformed it, the first successful seeding. Around the world today, dozens of rainmaking operations are in progress. How does the pioneer judge the possibilities?
Under the right conditions, it is quite feasible to get a 20% increase in the precipitation from a cloud system. And we have evidence now that hail and other severe storms can be modified. I think the time is rapidly approaching when we will be able to no longer depend on the vagaries of the weather, but perhaps can do something about it. It may be easier to control the weather than to forecast it.
But unless you can forecast how clouds would behave naturally, how can you be sure that you've really controlled them? Humpy cumulus clouds, like these over Florida, are prime targets for the hopeful modifiers of the weather. The U.S. government's environmental research laboratories have long-running trials in progress. Joanne Simpson and William Woodley are trying to settle a vexing issue. Can human beings, by seeding clouds, genuinely alter them to a worthwhile extent?
Can we turn back in here, or is it too close? How about a 270 to the left?
Okay.
Outside the aircraft are mounted the silver iodide flares that help ice to form in clouds. But they don't necessarily fire when the order's given. That's decided by drawing a card at random, saying whether to seed or not. Today, the card says seed, but the experimenters up in front, as they select their clouds, don't know that.
Okay, Fritz, you ready?
Ready?
Fire 1. Fire 2. Fire 3. Fire 4. Fire 5.
They must judge any growth that occurs in the cloud without knowing whether they've really seeded it or not. That's to avoid bias.
Fire 6. Fire 7. Fire 8. Fire 9. Fire 10.
Only thorough statistics will convince the skeptics that rainmaking really works. Stationed across the Florida farmland, rain gauges give some evidence of increased rainfall directly under the seeded clouds. But does the seeding really make more rain over the target area as a whole?
Okay.
After 37 days of experiments spread over 4 years, Dr. Simpson and Dr. Woodley still can't say one way or the other. They need another 60 days in the air. In any case, nothing that humans do can yet compare with nature's casual building of a thunderstorm over the mountains of New Mexico. We're seeing it speeded up 100 times.